So we are now talking about ionic bonding, right? So I am just taking an example of sodium and chlorine, which will form an ionic bond, right? So if you see the sodium and chlorine, the sodium has a tendency to give away one electron, and chlorine has the tendency to gain that one electron, since it has only 7 outer orbit electrons. So once it gains the next one, that will achieve the 8th electron. So that will be stable, right? So sodium and chlorine, in order to gain the stable energy state, they are transferring electrons in between them, right? So while transfer, sodium loses its one electron and chlorine gain that particular electron, right? So now due to this, there will be an attraction between them, right? There will be an attraction between these two, right? Since it is giving and it is gaining, there will be an attraction. At the same time, sodium has already 10 electrons in the inner orbitals. So the first two, they won't have any problem, but the other one would be the last orbit. So now the sodium and chlorine, they does have some last orbit electrons. So that's what I am showing here, right? Sodium also will have 8 outer shell orbit, and chlorine will also have 8 outer shell electrons. So these electrons, they will try to repulse these two, right? Due to this electron, when they are coming closer, the already available electrons, they will try to repulse. So here we have the attraction energy, and here we have the repulsion energy, right? So once this attraction and repulsion and everything is over, we will have this net energy. So that is the total energy. So what I have shown in this blue dotted line here is the attractive energy, right? So attractive energy can be denoted by EA. Okay. Similar way, what is shown in this green dotted line is the repulsive energy, right? Repulsive energy. So that is this ER, right? Sum of these two, the attractive energy and the repulsive energy, will be the final energy En. So net energy would be the sum of EA and ER, that is attractive and repulsive energy, right? Now this attractive energy can be written as minus A upon R. So this is a standard formula, right? Minus A upon R. Similarly, this repulsive energy can be written as minus B upon R to the power n, right? And this A and this B are constant numbers, while this R is the interatomic separation, right? So interatomic separation means the distance between the atoms of those two elements which are now being bonded, right? So now our case is sodium and chlorine. So sodium and chlorine. So if I consider this is the atom of sodium and this is the atom of chlorine, the distance between these two atoms is the R, right? So that is this R, interatomic separation R. So I am drawing a graph between R and energy E, right? Energy E. So repulsion energy I will take positive and attraction energy I will take negative, right? You can take in the otherwise also, right? Usually we take like this, right? So then we'll draw a graph. So attraction energy graph is minus A upon R, right? Minus A upon R. So there, if you draw this blue dotted line is the graph, right? So it will go like this, right? And here, if you see the repulsive energy, equation is minus B upon R to the power n, right? So if you draw that graph, it will go like this, right? So this B upon n graph is more closer than this one to the x-axis, because it is to the power, right? So if you want to check, you just can take your copy and you can write, just you put arbitrary numbers, right? So A and B, you keep it constant, right? And for R, you put like 0.1, 0.2, 0.3, 0.4 and observe what will happen to the equation, right? Since it is R to the power n, this is too closer to the x-axis than this one, right? So the net would be on the attractive side, right? Net will be on the attractive side. In this particular graph, there is a certain energy level where the energy is minimum, right? The energy is minimum, which we call it as E naught, right? This is the balance energy. of this minimal state while these two forming the bond, right? In order to achieve this level, they form the bond, right? So there are a few examples for ionic bonding, right? So I told you usually those at this end and those at this end will form the bond, right? Usually, right? So in the left hand side, you see we have sodium, potassium, rubidium, cesium, francium. In a similar way, magnesium, calcium, strontium, barium, and radium. So these all will lose 2 electron since they are in the second block, and these second column, and these all will lose 1 electron. In the similar way, these at the 7th column will acquire 1 electron, and these at the 6th one they will acquire 2 electrons, right? While this one they does not have any reactions at all, right? So here give up electrons this way, and here this way acquire electrons. So this is how the ionic bonds are formed, right? So there are a few examples. NaCl. So on this side we have Na, which have 1 electron, and this side I have Cl, right? Cl, which also need 1 electron, so they will form NaCl, right? And there you see Mg, which will lose 2 electrons, and O, which will gain 2 electrons, so that will form MgO, right? And here we have calcium, which will lose 2 electrons. Yeah, so in that case, so calcium 2 plus, so which will lose 2 electrons. But this fluorine, right? Fluorine is over here, that will gain only 1 electron, right? F minus, right? So it has given 2 electrons, but this F can't take those 2 electrons. So what will it do? It will call another, right? And now these 2 fluorine will give the gain this electron. So 1 electron will be given for this F, and 1 electron will be given for this F, right? So here we have 1 calcium and 2 fluorine. So we will write it as CaF2, right? 1 calcium and 2 fluorine. In a similar way, if I write for K and O, right? K and O. So potassium, you see, it will lose 1 electron, right? So 1 plus. O will gain 2 electrons, right? So this potassium is not enough to supply enough electron for this O, right? Because it can supply only 1 electron. So what will happen? Another potassium will come to supply the other electron to this O. So now we have 2 potassium, so K2 and 1 oxygen, right? So this is how the ionic bonds are formed, right? So if it is losing 1 electron and gaining 1 electron, that's fine. NaCl. Losing 2 electron, gaining 2 electron, that is fine. MgO. The CaF2, it is losing 2 electron, but F can gain only 1 electron, so it will call for another F. So those 2 electrons will be given, one for this one and one for that one. So now CaF2. Like that, K will also K2O. K can supply only 1 electron, but O can supply. O can gain 2 electrons. So now it is K2O, right? 2K for 1O, right? So this K will supply 1 electron for this O, and this K will supply 1 electron for this O. So 2K is supplying electron for this O. So that is K2O, right? So 2K and 1O. Then we have the second primary type of bond is covalent bonding, right? So in the previous case, what we saw is transferring of electrons. So one will gain and the other one will lose. In the case of covalent bonding, there won't be any electron transfer, but there will be electron sharing, right? So covalent bonding, we'll see similar electronegativity, share electrons, right? So I told you, in order to the ionic bond to occur, we need the electronegativity difference a kind of little bit high, right? But in the case of covalent bond, it need not to be that high, right? Even similar electronegative elements can form covalent bonds, right? Therefore, sharing electrons. Bonds determined by valence s and p orbitals dominate bonding, right? So again, we need this s and p in order to check whether it can form a covalent bond or not, right? So here we take an example of CH4, right? CH4. C is our carbon and H is hydrogen, right? So we have 1s2, 2s2 and 2p4, right? No, 2p2. And hydrogen has 1s1. Okay. So in this case, 1s2 for carbon is fine, but here 2s2 and 2p2 is there. We need 8 to be stable, but we have only 4. So we need 4, right? We need 4 more. And hydrogen, it has 1s1 electron level. In order to be stable, it needs 1 more electron. So that is, then it will gain the status of 1s2, right? 1s2. Now, so hydrogen need 1 electron, carbon need 4 electrons, right? So what they will do, each hydrogen atom, so these 4 at this region, they are hydrogen atom, they will come closer to carbon. So already this hydrogen has 1 electron. Now it is shared with the carbon, right? Similar way, this way. So hydrogen sharing its electron with carbon and carbon sharing its electron with hydrogen. This is happening in all 4, right? All 4 hydrogens sharing their electron with carbon and carbon sharing its own electron with the hydrogen, right? So after all this, if you see, hydrogen has 2 electrons. So 1 electron is hydrogen's electron, other one is carbon's electron. So it is shared, right? It is shared. Similar in all 4 regions, right? So now all hydrogens achieve the 1s2 stable energy level. So 1s2 is helium's, right? Helium's electron configuration, which is so stable. If you see carbon, it has 1, 2, 3, 4, 5, 6, 7, 8, right? 8 electrons. So now it is 1s2, 2s2, 2p6. So that is here 8 and here 2. That is neons electronegativity. Sorry, not electronegativity, neons electron configuration, right? So this is also stable. So in order to achieve this stable state, what these elements usually do, they will share electrons. So this CH4 is just an example for the sharing. So the electronegativities can be similar in the sense it need not to be too high or too low. It can be nearby that, right? So if you see where's electronegativity values, here we have. So hydrogen it is 2.1 and carbon it is 2.5, right? Only 0.4 is the difference. So we don't need any much more electronegativity difference. Primary bonding. Metallic bond delocalized as electron cloud. So the bond which formed between metals, right, which is called as metallic bond, right? Say for example, a sodium or potassium, right? So these all are metallic bonds, right, between metal and metal, right? So if there are a metal bar, then the atoms join there by metallic bond, right? And if the bond formed between a metal and non-metal, usually that would be a ionic bond, right? Not necessarily all the time. Most of the time that will be a ionic bond, right? And if the bonds formed between a non-metal and non-metal, most of the time that will be a covalent bond, right? And here you see ionic covalent mixed bonding. So I told you why the electronegativity is necessary. Pauling's electronegativity is in order to find the ionic character. So how much the bond is ionic. So there only we can decide whether it will show the ionic properties or covalent properties, right? Ionic properties or covalent properties. So I am just doing an example, right? Taking MgO, right? So this is a formula, percentage ionic character 1 minus e to the power minus xa minus xb whole squared upon 4 into 100, right? So in order to find the percentage, we will multiply by 100, where xa and xb are Pauling's electronegativities, right? xmg and xo, right? So you see the electronegativity table, magnesium, it does have the value of 1.3, and oxygen, it does have the value of 3.5, right? So since it is a whole squared, whether you take xa is magnesium or xa is O doesn't matter, right? Even if you interchange these two, you can find the answer. So you can put xa is equal to 3.5 and xb is equal to 1.3, or else you can put xa is 1.3 and xb is 3.5, doesn't matter because it is a whole thing squared. So at the end, that will form a positive value, right? So that positive value divided by 4 multiplied by minus will be minus value. So e to the power minus is a 0 point value. So 1 minus 0 point will give you a 0 point value, right? So always this ionic character value will be in between 1 and 100, right? So MgO 3.5 minus 1.3 whole squared upon 4. So if you take your calculator and count, that will bring 70.2% ionic, right? 70.2% ionic. So this is the ionic character of the MgO, right? So this is how we find the ionic character by this formula. Substitute these two values, the Pauling ionic negativity values, then you will find the ionic character, how much it is ionic, right? So MgO is 70.2% ionic. So in case if you have something from this side, right, maybe the first line, and something on the 7th line, you will have more ionic character, right? Because here and here the difference is so high, right? So you will have more ionic character. So okay, so these all about primary bonding. Now we have secondary bonding, right? Secondary bonding, there are a few types of bonds, right? Arises from interaction between dipoles, right? So we'll see what are these dipoles. So if we take this hydrogen, right, liquid hydrogen, right, liquid hydrogen, it has H2, right? 2 H atoms are there, right? So once they share the both atoms, they would become H2, right? Between one H2 liquid molecule and another H2 liquid molecule, there should be some connection, right? Some attraction. Otherwise, they will not stay together. No? So this length is the dipole bond, right? So in one H2, there are 2 hydrogens are there, right? So these 2 hydrogen, right? So if I assume this as 1 hydrogen and this as 1 hydrogen, right? When you know if there should be a bond, then plus and minus can form a bond, or minus and plus can form a bond. Minus and minus will try to push each other. Similarly, plus and plus will try to push each other, right? So they will try to push each other. Minus and plus, so plus and minus will try to come closer. So when these two come closer, in hydrogen, that molecule, if the minus pole is coming towards this side for a bond, the other hydrogen, right, other hydrogen molecule, automatically the plus side will come in order to form this bond, right? So what will happen in this hydrogen atom? These ions will move for other side which are far from this hydrogen. If you see, so now this plus and this plus have this much length, right? Similarly, this minus and this minus have this much length, right? So they are actually very far apart. But if you see this minus and this plus, they are closer to each other, right? So this would be the scenario in this dipole moment, right? Dipole moment. So this will form the bond, right? Dipole bond. So that's why it is mentioned as secondary bonding. So this is not that firm as ionic or covalent bond, right? This is not that firm, right? So these are kind of temporary adjustment, you can say. So when this one and this one are coming closer to form a bond, automatically this plus side of this molecule and minus side of this molecule would come closer, pushing the positive, or I mean pushing the same atoms far apart. So this plus and this plus are far. So this distance is higher than this distance, right? Oh, this distance is higher than this distance. So they will push them to go for a further side so that they will form a bond, right? So similarly here, so this H2 and this H2, this is how they form the bond. So this H2, this is covalent bond, right? This H and this H are covalent bond. This H and this H also covalent bond, right? But when this H2 and this H2 come closer to form a kind of liquid hydrogen, at that stage, these, if this part, I mean this phase, this region, if it is plus, right, if this region is a kind of plus, then automatically this hydrogen will send this plus part back and minus region would be coming forward to form this bond, right? So this is how dipoles are formed. That's why it's mentioned fluctuating dipoles. They are not firm, right? They can alter their electrons according to the necessity, right? So that's why it is mentioned fluctuating dipoles. Asymmetric electron clouds. You see, asymmetric electron clouds. So asymmetric means they are not symmetric. So if you take the electron distribution of this H2 atom, not atom, molecule, and this H2 molecule, the distribution of electrons would not be similar, right? Same. For this H2 molecule, electrons would be this part and protons would be on the other part. But in this H2 molecule, protons would be on this part and electrons would be on the other part, right? So they two are not symmetric. So that's why it's mentioned asymmetric electron clouds, right? So here the electron cloud would be on this region. That's why it's minus, right? Here electron cloud on that region. So that's why this region is minus. So if this region is minus, right, then another H2 atom which is coming closer to form the bond, it can have positive region here, leaving negative region here. So this positive region and this negative region can form a bond, right? So the scenario would be something like this. They would form bonds like this, right? So this is how the liquid hydrogen bond achieved. You know, liquid hydrogen cannot be achieved in normal usual pressure and temperature, right? So there are certain degrees Celsius, I think some around -200 or -180 or something like that. We need to reduce the temperature as well as, and there are certain value for pressure also, right? So on such a certain sequence only, this liquid hydrogen can be formed, right? So simply you can't form it in the room temperature. So by just allowing few hydrogen gas atoms to in a bottle or some container, you can't form the liquid hydrogen bond, right? So it needs some specific conditions. Some low temperature and low pressure is necessary in order to form this liquid hydrogen bond. Right? On that particular situation only, this can be achieved. The electron clouds need to be pushed to one side and protons need to become to the other side, and they need to form a kind of bond. So that is why fluctuating dipoles is mentioned, and dipole bonds are very weak and mentioned as secondary bondings. Because if you see the ionic or covalent bond, you don't need all these things, right? Pressure is not necessary, temperature you don't need to worry. You just have to keep the plus ion and minus ion side by side, then that will find a way to form the bond. But here that's not the case. They will not find their own way to form a bond. We need to provide with enough support, right? Pressure, temperature, those are the supports, right? This is the fluctuating dipole, and here we have another one, permanent dipole, molecule induced, general case, right? So this is for hydrogen, and this one is the example for HCl. So HCl, what do you know about HCl? So HCl is a acid which is hydrochloric acid. They are highly volatile. So when you open the HCl bottle, that would be capable of evaporating, forming HCl vapor, right? Permanent dipole molecule induced. So here we have two things. One hydrogen is there, one chlorine is there, right? So if I draw, I have an H here, I have chlorine. Yeah, so this 5, right? This 5 plus this 2 will form the outermost, right? This 5 and this 2 will form the outermost. So that is 7 is the outermost, because here also 3, this is also 3. So in third shell, we have subshell S2 and subshell P5.
Yeah.
So altogether in outermost shell, we have 7 electrons. In this subshell only S2 and P5. So what we are writing this 3 is to confirm that is in the third orbit, and then we as a breaking it into small parts S, P and D. And sharing of electron, it has 1, 2, 3, 4, 5, 6, 7, 8. So 8 electrons. Chlorine have 8 and hydrogen have 1, 2, right? So now both of them are in stable stage, right? Both of them are in stable stage, right? Right, this thing is fine. For now, what we need to do is, we are going to see how is this permanent dipole is going to be happen, right? So normally, chlorine have more number of electrons, so that would be more negative in nature, right? More negative in nature since it has more electrons in the outer shell. Similarly, hydrogen would be positive in nature, right? Because it has only 1 electron. So comparing to chlorine, hydrogen is positive in nature, first thing. Second thing, hydrogen is a small molecule compared to chlorine, which is a kind of large molecule, right? When these two form a covalent bond, hydrogen compared to chlorine will be in a kind of plus state, and chlorine compared to hydrogen will be in a negative state, right? So similar case would be applicable for another HCl molecule also, right? So where there will be a chlorine and there will be a hydrogen. So hydrogen would be positive compared to chlorine, and chlorine will be negative compared to hydrogen. So these two HCl molecules, while forming the liquid, will come close together. So I told you hydrogen is a kind of positive compared with chlorine. So this positive and this negative will form a bond, right? These two will form a bond in between them, right? So this is a reason for permanent dipoles molecule, right? Permanent dipole. So why this is permanent and this is temporary, is fluctuating, is room temperature and pressure is enough for this hydrogen, HCl, to be in this liquid stage, right? Room temperature and pressure are enough. But in this case, right, they are not enough, and we need to support, or we need to give some additional conditions so that they will acquire that liquid stage, right? If we remove those conditions, right, so this is like living with the life jacket. So if we provide life jacket and oxygen and everything, this will survive like this. If you remove this will again turn to hydrogen gas, right? So that's why this is called as fluctuating dipole, and this is called as permanent dipole, right? Then we have polymer secondary bonding. So about polymer, I have a complete chapter. Properties from bonding, right? So there are certain properties which can be determined by the bondings, right? So we'll see one by one. Bond length R, right? So bond length R, I told you it is the distance between the two atoms of these two elements which are on the bond, right? So if it is Mg and O, it can be Na and Cl, or it can H and H. So whatever the two elements which are on bond, the distance between these two atoms of those elements are the bond length R, right? And then I have the bond energy E naught, right? So E naught is the bond energy, which is the minimum energy needed to form a bond, right? So this one also I have already explained. So there would be like two forces, one attractive and one repulsive force. When you combine these two forces, you will have an resultant force. So that is this resultant force curve, right? So this spot is the bond energy spot where this E naught is minimum, right? And then I have melting temperature Tm, right? Tm is the melting temperature, Tm melting temperature. So melting temperature is again directly proportional to the bond energy. So if the bond energy is high, again the melting temperature will be high. So melting is what is melting? Breaking the bond and making it into liquid phase, right? So if it is metal or non-metal, that doesn't matter. To break the bond and make it into liquid state is the melting. So in melting, you need to provide some energy. That energy is quite dependent on this bond energy, right? So if this bond energy is high, then your melting energy need to be high, right? So that's what mentioned by here. So larger Tm, right, and smaller Tm. So if the bond energy is low, then lower Tm, that is melting energy, is enough to melt it. If the Tm, that is melting time, if the bond energy is high, then you need to provide high energy for the melting of this bond, right? Tm is larger if E naught is larger, right? So when this E naught keep on large, this Tm, that is melting temperature, will be also kept on increasing, right? So in other words, you can say melting temperature, that is Tm, is directly proportional to bond energy E naught, right? So if Tm is increasing, sorry, if E naught is increasing, then Tm will increase, right? Bond energy increase, then melting temperature will also increase. If bond energy decrease, then melting temperature will also decrease, right? So these are few properties which you can gather data from the bonding. Okay, then there are certain other properties also, right? Coefficient of thermal expansion alpha, right? So you know metals are subjected to expansion while heating, right? If you heat metals, they will expand either in length or width or volume, they will expand. So here we have a metal, right? So length L naught is the actual length, right? Length L naught is the actual length, unheated, right? Unheated. So before heating, we keep it as T1, right? That is T1. So when you provide some heat, the length of the metal is increased up to here, right? So this increase in length is the delta L, right? So delta L, we call it as increase in length. So here that is heated time, that is temperature is T2. So we provide some temperature and that temperature is T2. So the length of the new, actually the new length of the element or metal would be calculated by this formula, right? So delta L upon L naught is equal to alpha into T2 minus T1, right? So this delta L is this delta L, right? That is increase in the length, and L naught is the actual length. So before heating, we have this length will be equal to alpha, right? So this alpha is a coefficient of thermal expansion. So this is different for different material, right? So I think it is very high for aluminium, and then it is reducing. So each element have different coefficient of thermal expansion, right? So that is alpha into delta theta or T2 minus T1. So T2 minus T1 is the temperature difference. After heating, what is the temperature, and before heating, what is the temperature, right? So this will give you the new length, right? New length in the sense increase in the length, right? So you can use this equation to find if you know the temperature and alpha, so that you can find how much it is increased in length. So the width will also increase. So at the end, you will have a delta W added, right? So if this is your initial width, right, and maybe after heating this would be the width, right? So there will be a smaller part delta W, that is the increase in the width. Okay, so this is a small comparison between ceramics, metals, and polymers, right? Just a kind of comparison. So when we study these polymers and ceramics, we will go deep into that. Ceramics, it can either be ionic or covalent bonds. So silica is SiO2 covalent bond, something like that. So we have both covalent and ionic. Large bond energy, right? Bond energy is large. So if the bond energy is large, again melting point is large, energy is also large, right? In order to form the bond, small alpha. Metals, we have variable bond energy, right? So based on where the metal is situated, whether in the first column or second column or in the D block, so it will vary. Moderate Tm, moderate E, and moderate alpha, right? So all are moderate. So they are just outlined. They are not as you don't think like exactly it is the case. There are some cases that will fall out of these boundaries. This is just common assumption, right? And polymers, covalent and secondary. So this will have both covalent bond as well as secondary bond. Secondary bond in the sense dipole and all, right? Directional properties. So directional property, I will say what is it in the polymer section, right? Secondary bonding dominates, right? So secondary bonding dominates. So in this case, primary bond is next to the secondary bond. Next in the sense, the dominant features will be acquired from the secondary bond. Small melting point, small E, and large alpha, right?